Hi everyone, it's Mrs. Hallman, and we are going to learn a little bit about the expectations of graphing here at YSHS. Today, essentially, you're going to be learning how to graph like a guru. We're going to teach you a couple things that you might have learned in other years of science class, but we're just kind of making sure that we outline the level of expectation that we require here at the high school, and we'll be graphing a lot this year in science. So you want to make sure that you keep these tools in mind as you go through. Definitely have out a piece of paper and be ready to learn. Here we go. So what we're going to do is I wanted to start with just a quick question of what you think about this graph. So you should be able to see on my screen that this is definitely a graph. And if you look at it, I'd like you to take a couple moments and to yourself think about what information can we learn by looking at this graph. We call that extrapolation. So what meaning can we learn about this graph? Okay. Okay. Now, most people, when they look at this graph, they know that the topic of the graph has something to do with speeding tickets. Then students usually say, well, something is going up, right? We can see that there's a general progression of the line going up. But in terms of what we're looking at, there's not a whole lot else to go on. You notice that both of our axes, we don't really know what the 1 to 200, or sorry, the 0 to 200 is, or what the 10 to 100 is on the bottom. So that's pretty much all we can learn about from this graph. Which brings us to our second question. Is this a good or acceptable or proper graph in this level of science? And hopefully right now you are saying no, that this graph is missing, lacking quite a lot. So go ahead and answer to yourself, what type of graph is this? You might have learned in other years how to classify or categorize when to use each type of graph. And what type of graph is this? And if you answered that this is a line graph, you are correct. The fourth thing is, to yourself, see if you can pick out 4 things that this graph might be lacking. 4 things that either it's lacking, or 4 corrections that you would make to make this an acceptable graph. So take a look at it and to yourself, try to pick out 4 things that you know we could do better on this graph. Excellent. Okay, so most people notice right off of the bat that each side of our graph, our 2 axes, our x and our y axes, those are not labeled. So we don't know what 0 to 200 is. We don't know what 10 to 100. So that's 2 things that are definitely missing. 2 other things that go along with labeling the axes is that we're missing some units. We don't know what the numbers 0 to 200 represent. We don't know if that's dollars. We don't know if that is miles per hour. We don't know if that's people. We don't know if that is percentages. All right, so definitely lacking a lot of things. And I'll also say the other thing we're lacking is a proper title, because while this graph has a title, it's not a proper scientific title. All right, so let's dive into this and let's figure out how we might be able to kind of rework this graph to make it a proper scientific graph. First thing you always need to remember when graphing here at YSHS is that every graph needs a proper title. And regardless of whether or not you're in bio class or chemistry class, a proper scientific title should always have 2 things. It should have what we consider the independent and the dependent variables. So sometimes in chemistry class, you might say the effect of temperature on the volume of gas in a vial. So it's always appropriate to say the effect of blank on blank, because both of those would be your variables. So let's see what this graph would look like if we would include a more proper title. Right? So this title now says the dependence of traffic ticket costs on automobile speed. The reason why in science we require both variables is that all of a sudden, even without proper labels on our graph, this title has already told us something about this graph, and we can already start to extrapolate or learn new things from it. So we know that one of these axes has something to do with traffic ticket costs, so how much that traffic ticket would end up being that you'd have to pay, based on automobile speeds. Basically, the faster you go, the more your traffic ticket is going to cost you. So that would be an example of a good scientific title. So this year, as we graph together, just always go back and look and make sure that you have both independent and dependent variables in your graph. All right. Now, second thing to help you graph like a guru, to always have a good scientific graph, is that you need to always label our x and our y axes. All right, so we learned probably in other math classes up to this point, maybe other science classes, that the vertical line on our graph is called our y-axis, and the horizontal line is called our x-axis. So each axis needs to have a label, and it also needs to have proper units in the metric system. So always in science class, which this is a little bit different than in other classes, but always in science, we convert to the metric system because it's so much better. So let's take a look at this graph if we were to add the proper x and y axes and units. So here would be our y-axis, and now we're saying that this is the cost of average speeding ticket in dollars, okay? And our x-axis is going to be our automobile speed. So already, just adding a proper title and the correct axes, labels, and units, we can start to extrapolate a lot from this graph. We can see that as the automobile speed increases on our x-axis, the cost of that average ticket is going to increase as well. Okay, so let's get down to what these axes represent. All right, and if you are in my classroom, I encourage you the next time you're in class to look at the top right-hand corner of where my whiteboard is. And you'll notice that swinging from the ceiling, hanging from the ceiling, is an empty container of Lipton iced tea. And the reason why I keep that up there is for a visual reminder of an acronym that will help you always place the correct variable on the correct axis of the graph. So the x-axis of a graph always has to be your independent variable. And this is true in chemistry and physics as well. The y-axis, which is the up and down vertical axis, always has to be the dependent variable. And we keep these the same so that in science we can always look at a graph and we can extrapolate what that experiment was about. What does this have to do with an iced tea container? Well, on your screen you can see a really, really clever and useful acronym that I refer to a lot and that other science teachers here at YS use as well. And that's dry mix. So inside of that Lipton iced tea container, there is a dry powder that when you mix with water makes iced tea. But I always remember dry mix. So DRYMIX stands for dependent results y-axis. So if you want to simplify it even more, just remember D and Y, that your dependent variable will always go on your y-axis. How handy is that? And that the mix part of it is your independent variable will always be on your x-axis. So you can always remember that the independent variable is the one that the scientists will change or manipulate. So that M helps you remember that as well. So always remember dry mix when you are creating your graph, all right? The fourth clue for how to graph appropriately in this science class is to always fit the type of graph to the task that you're trying to do. So primarily in biology class, we'll use four main types of graph this year. So those are the four we're focusing on right now. The first of which is a line graph. So line graphs we typically in bio will always use whenever time is involved. So if we're measuring the amount of heartbeats in a 5-minute period, since time is ongoing, it's continuous, we will use a line graph to represent that. Line graphs are very helpful to show the progression of events. So maybe average sale of t-shirts over many years. The second type of graph we'll use is bar graphs. So this is whenever in bio we have categorical data. So if we are comparing population densities of multiple discrete and separate species, we might choose to use a bar graph so that we can compare our individual categories. Bar graphs wouldn't be as acceptable to use to compare over time, since time is ongoing and it's harder to kind of have separate categories of time. So bar graphs can be very, very effective at showing different categories and how they compare together. Scatter plots we will also use quite frequently. So scatter plots are kind of like collecting all of the data points from an experiment and throwing them up onto a graph to try to find trends and extrapolate data from those points. So if you were to look at all of those red scatter points on a chart in a data table, you might not really see any trends because they kind of seem randomized. But if we look at that scatter plot that's on the screen now, you can see that there's actually a positive correlation, meaning all of the points collectively will kind of go in one direction. Scatter plots are also where we typically would use the idea of like a line of best fit or a correlation line, where we would either graph or electronically plant in a line of best fit, and then from that line we could then extrapolate other data points to make predictions or to better interpret that data. The fourth type of graph that we will use a little bit this year, we don't use it as heavily as perhaps a math class would be a pie graph. And essentially pie graphs are only used whenever the data that we're looking at is percentage based. So if we are ever in an experiment measuring something and then calculating the percentage of that particular data set, then we would probably opt to use a pie graph. You'll also find that sometimes it's helpful to have two different types of graphs, to look at them both and to decide which graph most accurately and most usefully displays the data that you're looking at, okay? The last thing we'll talk about is just the scale that you use on your graphs. What we'll learn in a little bit is that graphs and data that is on a graph can easily be manipulated or skewed to have a lot of different effects. And we see this a lot of times in the media, where graphs will be a little bit shifted to have a more desired result. So it's important in science that we not only know how to graph, but we can also be skeptical of graphs that we see in print or magazines, and we can understand whether or not that graph has been skewed. And a lot of times the way they do that is by choosing an inappropriate scale for the axes of your graphs. One thing we do in science is that we typically would like to see that our data is graphed as largely as possible. So we don't want a huge graph and then to have all of our data points all shoved up in the top right-hand corner. We want to see the progression of those data points, generally speaking. So if we revisit that original graph, we can see we have our proper title, we have our axes labels. It looks like the scale is good. When I look at this, this is a line graph, so it's showing a progression, it's showing a trend line. I can see that my scale is appropriate. Not all the data points are all shoved up into one corner. I can see how that correlation between cost and automobile speed is there. Plus, I can see that the units for automobile speed are in kilometers per hour, not miles per hour, because it is a scientific graph and we are always going to convert to the metric system. So all of these things are tools and 5 things that you need to check to make sure that you always include in your graphs. You'll be practicing these not only this year in bio, but other years as well. If you go into chemistry or physics or integrated science, you'll be graphing in those classes as well. So if you get these techniques, these tips into practice now, they will help you in the long run. Guys, I hope that was helpful, and please let me know if you ever have any questions.